Principles of flame photometry. Flame photometry is a spectral technique in which excitation is caused by spraying a solution of the sample in a hot flame. Flame can serve both as a source of atomic emission lines and also as an absorbing medium for the same lines. Flame photometry is concerned with the emission of characteristic radiation in flames by individual atom elements and the correlation of the emission intensity with the concentration of the element introduced in the film. Flame photometry coupled with readout devices produces a high sensitivity and high reliability for the determination of several elements. The technique is widely acceptable for the analysis of sodium and potassium, especially in fluids and tissues. Flame photometry is different from atomic absorption spectroscopy in respect that the former is based upon the behavior of particles that exist in the ground state in the film, whereas the latter is concerned with those particles that are electronically excited in the medium. Let us see the specific principles involved in the flame photometry. Now, when a sample is sprayed into the flame, phenomena which occur in rapid succession are as follows. The first and the foremost phenomena that takes place is the evaporation of solvent, leaving behind a solid residue. The second phenomena which occurs is the vaporization of the solid, followed by its dissociation into its constituent atoms, which initially will be in the ground state. The next phenomena which occurs is that some atoms may be excited by the thermal energy of the flame to higher energy levels, and they attain a condition in which they radiate energy. The resulting emission spectrum thus consists of lines originating from excited atoms or ions. The neutral atom spectra, they are of main interest in the flame photometry. The spectra which is due to ions may be produced at high temperatures and high concentrations of the atoms in the flame. If we look at the equation below, now suppose if E2 and E1 represents the energy of higher and lower energy levels concerned, the radiation emitted during the transition can be defined as E2 minus E1 is equal to h nu, or nu is equal to c lambda, where E2 minus E1 is equal to hc upon lambda, or lambda is equal to hc upon E2 minus E1. We can call it as equation number 1. From this above equation number 1, it is possible to evaluate the wavelength of the emitted radiation. Now, this radiation is characteristic of the element which emits. The intensity of radiation corresponds to the amount of element which is present in the flame. If you look at the diagram below, we see that first of all it is a reversible reaction. We have evaporation of droplets which changes into solid MX. The solid undergoes vaporization and forms MX gas, which dissociates into individual constituents, and on thermal excitation becomes an ion. The temperature of the flame usually lies between 1000 degrees centigrade to 3000 degrees centigrade. Now, the sequence of events which have been shown in the figure, they normally occur in flame photometry. A portion of the neutral atoms or radicals formed in the flame, they may combine to form a new gaseous compound. Now, the fraction of free atoms that are thermally excited are governed by Boltzmann distribution, which is as follows: n asterisk upon n0 is equal to g asterisk upon g0 exponential minus delta E upon kt, where n asterisk represents the number of atoms in the excited state, n0 is the number of atoms in ground state, g asterisk upon g0 is the ratio of statistical weights for a ground and excited states. Delta E is the energy of excitation, which is equal to h nu. K is the Boltzmann constant and T is the temperature in Kelvin. Now the ratio n asterisk upon n0 is dependent upon both the excitation energy delta E and the temperature T. An increase in temperature and a decrease in delta E will result in a higher value for the ratio n asterisk upon n0. Now, if only a small fraction of the atoms are excited, even under the most favorable conditions, that is when the temperature is high and the excitation energy is low. Absorption spectra of most elements are simple in character as compared with emission spectra. It therefore follows that atomic absorption spectroscopy is less prone to inter-element interferences than is flame emission spectroscopy. In this respect, the wavelength of the resonance line is a critical factor. Elements whose resonance lines are associated with low energy values are more sensitive as far as flame emission spectroscopy is concerned than those elements whose resonance lines are associated with higher energy values. Thus, sodium with an emission life of wavelength at 589 nanometer shows great sensitivity, whereas zinc with emission line of wavelength 213.9 nanometer is relatively insensitive. The integrated absorption will then be given by the expression K dV is equal to F n0 pi exponential square upon mc, where K will represent the absorption coefficient at frequency nu, E is the electronic charge, m is the mass of electron, C represents the velocity of light, and F represents the oscillator strength of the absorbing line. Now this is inversely proportional to the lifetime of the excited state, and N0 will represent the number of metal atoms per ml which are capable of absorbing the radiation. Integrated absorption coefficient is directly proportional to the concentration of the absorbing species. To summarize, flame emission spectroscopy requires the production of excited atoms in the vapor state. The conversion of solid MX into gaseous metal atoms is governed by factors such as rate of vaporization, flame composition, and flame temperature.